Advancing Cybersecurity Science, Engineering and Technology. Welcome to ISAUnited's Defensible 10 Standards Foundations and Practicum. Our mission is to elevate cybersecurity into a true engineering discipline, where designs are justified, outcomes are measurable, and security stands up to adversarial scrutiny. Here's our path for today. We'll begin by introducing ourselves and explaining our purpose. We'll define the problem in our industry and the solution we propose. Then we'll introduce the Defensible 10 standards, walk through what's inside a standard, and demonstrate the journey using network security as our worked example. We'll close with verification and validation and practical implementation guidance. About ISAUnited.org. Since 2019, ISAUnited has operated as the first standards development organization dedicated to cybersecurity architecture and engineering. Our charter is simple and demanding: produce defensible technical standards that go beyond compliance checklists to deliver engineered security. Defensible 10 standards. Compliance proves audit readiness, not real-world resilience. The Defensible 10 standards change the center of gravity from reactive, tool-driven practice to engineered security. Each standard defines what must be true before you begin, what must be produced by the build, and how that result is proven. Defensible 10 standards versus NIST and ISO. Many of you learned NIST and ISO. Those are foundational standards for governance and compliance. They tell us what to manage and how to show coverage. The Defensible 10 standards are technical engineering standards. They tell us what must be true before a build, what measurable outputs the build must produce, and how we prove it works. Controls implement those outputs. So the flow is: NIST and ISO sets direction, D10S defines engineered outcomes, and controls enforce them. That's how we turn policy into defensible architecture. The problem: in traditional engineering such as civil, mechanical, or structural engineering, there is a clear stack: foundational governance, technical standards from an SDO, design principles, codes and specifications, and control mechanisms. In cybersecurity, that middle layer, engineering-grade technical standards, has been missing. We've leaned on controls catalogs as if they were standards, and the result is uneven designs, inconsistent enforcement, and brittle outcomes. Our practice needs engineered requirements, specifications, implementation guidance, not just lists of controls. No technical standards body. In mature engineering, a standards body sets measurable baselines, interfaces, and tests. Cybersecurity has operated without that layer. We rely on controls and tools, not engineering specifications. The consequence is inconsistent designs, vendor-driven choices, and outcomes that cannot be proven. To fix this, practitioners must establish clear, testable standards so teams build the same thing the same way and can demonstrate that it works. Unbacked design principles. Design principles must set limits on how we build. If least privilege, zero trust, or encrypt in transit remain as policy lines, results vary by team. Make them concrete. No standing admin. Verify user and device on every access. TLS 1.3 everywhere with managed keys and scheduled rotation. Add simple checks to confirm each rule is in place and working. When principles are written as clear musts and verified, teams deliver the same outcome and drift is reduced. Controls without engineering. Controls are a must, but without engineering they become checkboxes. Examples: MFA without device or session binding, WAF on default rules, EDR agents installed but no isolation policy, logs stored but no detections. The fix: led with the standard, state preconditions, target outputs, and tests. Then map controls to those outputs and verify with automated checks and drills. That turns MFA, WAF, and EDR from settings into outcomes: verified identity, protected interfaces, and detectable, containable failures. Design without standards. Design without standards becomes a custom build or design every time. Teams rely on product defaults or individual preference, so the same term means different things across projects. Symptoms: missing preconditions, outputs that aren't measured, interfaces that break at boundaries, and changes that quietly undo security. The result is fragile systems and no consistent proof that defenses work. The fix: start from the parent standard, define required inputs before the build, measurable outputs after the build, and the guiding principles and mapped controls. Then verify so the same problem yields the same result. Build on vendor playbooks. Vendor playbooks are useful, but they're not your standard. They optimize for a product, not your architecture. When teams build from playbooks alone, designs become feature-led. Zero trust means different settings per platform, duplicate policy engines appear, conflict defaults occur, and gaps form at boundaries. The fix: define requirements and measurable outputs first, segmentation that blocks lateral movement, identity propagation end-to-end, managed keys with rotation, logging contracts, then configure each vendor to meet those outputs. Verify with cross-vendor tests so the design works regardless of product. V and V without requirements. Verification and validation. Without requirements measures activity, not outcomes. When inputs and target outputs aren't defined, teams run scans and tabletops on tool defaults. Dashboards look green while attack paths stay open. Examples: MFA on, but no device or session binding, encrypted, but keys unmanaged, segmented, but lateral movement still possible. Fix: write the requirements and acceptance criteria first, what must be true and how we'll measure it. Then, plan V and V, method, frequency, owner, and pass/fail thresholds tied to the output. Now tests prove the design, not just the tools. Missing SDO, weak links, indefensible architecture. When no standards body sets baselines, each team builds to a different idea. Interfaces are misaligned, trust paths vary, inputs get skipped, and outputs aren't measured. Weak links stack up, identity breaks across hops, and segmentation fails to stop movement. Detection becomes stored logs. We're guessing, we can't state what we engineered or prove it holds under attack. That's the cost of a missing SDO, a system we can't defend, predict, or audit. The solution: Defensible 10 standards. Orientation. We'll ground this journey in ISAUDSNS 1000, Network Security Architecture and Engineering. The network is universal and exposes every part of the lifecycle we expect in a defensible standard. Requirements, inputs. First, requirements. These are the preconditions you must verify before build work proceeds. Examples include a current asset and topology inventory, business-driven segmentation, a deny by default firewall posture, readiness for zero trust, operational NAC, modern secure protocols, integrated logging, and documented change control. Each input is evidence-based. If it isn't verified, the design isn't defensible yet. Technical specifications, outputs. Next, the outputs. The engineered outcomes you must be able to measure after implementation. Segmentation that actually limits lateral movement. Deny by default rules with inspection. Zero trust at the point of access. Modern cryptographic transport. And integrated detection and response. These are not suggestions. They are observable, testable specifications. Cybersecurity core principles, ISAURP, standards are enforced by doctrine. Least privilege, zero trust, complete mediation, defense in depth, secure by design, fail-safe defaults, resilience and recovery, and evidence production. These principles turn configuration into engineering. They guide trade-offs and keep designs from drifting back into convenience. Foundational standards alignment. Defensible does not mean isolated. We align to NIST, ISAUnited, and other governance frameworks, so risk and compliance teams can trace decisions from architecture through audit. The difference is that ISAUnited standards add the technical depth, the measurable outputs, those frameworks do not spell out. Security controls mapping. Controls translate architecture into enforceable safeguards. Here we map engineered outputs to familiar anchors. CSA, CCM entries for segmentation and identity, CISV8 network hardening requirements, and OWASP guidance for API authentication and mediation. This keeps your designs defensible and your assurance arguments concise. Engineering discipline. Defensibility comes from discipline. Treat policies and configurations as code. Make every decision traceable. Prohibit ad hoc changes that bypass design. Substandards under the parent, like firewall rule management, must adopt the same rigor, version control, peer review, and automated checks. Associate substandards mapping. The parent standard sets the contract. Associate substandards offer in-depth implementation guidance for key focus areas, including segmentation, firewall engineering, zero trust, NAC, and NDR. Each inherits the parent structure: inputs, outputs, principles, controls, and discipline. Peer review ensures consistency and quality as these are developed and published. Verification and validation. Verification and validation are where claims meet evidence. Confirm that every specified control is present and functioning properly. Validate configurations against benchmarks. Peer review the architecture, segmentation maps, and boundary rules. Exercise the design with realistic scenarios and confirm that security does not break business services. When V&V is continuous, drift is detected early and corrected quickly. Implementation guidelines. Finally, practical guidance. Keep the playbook vendor agnostic and engineering focused. Train new practitioners with the same steps you expect in production. Document decisions and their rationale. When in doubt, return to the principles and prove results with evidence. Here's the recap. Traditional engineering follows a stack: design, build, validate, safe. Cybersecurity needs the same pattern. Start with NIST and ISO for governance. Add the missing layer: ISAUnited's Defensible 10 standards, the technical requirements, and measurable outputs. Use design principles to set limits on how we build. Then implement with controls. Controls are not standards, they enforce the standard. As we move up the stack, engineering depth and assurance rise. Verify the outputs are the same across teams. That's how designs become defensible. Defensible 10 standards closing. Defensible standards turn policy into engineered results. Across the 10 domains, each standard defines required inputs, measurable outputs, mapped principles and controls, and the V&V that proves it. Use them to design once, implement across platforms, and show evidence that holds up. Start with one domain, apply the micro-template, write the requirements and outputs, map the controls, and run the checks. Publish the results for peer review and iterate. Security without evidence is opinion. With defensible standards, we design it, build it, verify it, and defend it.